Hello, welcome to my talk about messing with Unicode. Here I will talk about some interesting aspects of Unicode which allows for some interesting ways in which characters are being rendered. Some of these ways have been used in the past to trick people into doing things that they didn't mean to, like opening an exe file thinking that it's a TXT or a PDF document, when in reality it isn't. I suppose these days there are better safeguards in place to that it is less easy for people to fall into such traps. But still, these tricks provide ample ammunition for pranksters to pull jokes on us. And we need to know that such tricks exist to know that what exactly hit us. And that's what I want to do in this talk. I became interested in this topic after the renewed interest around such things in Unicode after the publication of this article and PEP 672, which came out as a sort of a response to it with regard to Python relevant features. So I have divided this talk into three sections. One about glyphs, the actual symbols being used to represent the characters, and then about some effects brought about by the bidirectional algorithm of Unicode, and finally some ways which can be of some possible help to identify the presence of special characters that can make text look like it's something that it isn't. So let's get started with the first section about glyphs. So many of us must have come across a meme that goes something like this, where somebody's thinking of replacing all the semicolons in a language like C, which makes heavy use of semicolons, with a Greek question mark, which looks identical to a semicolon. So the Greek question mark does look like the one in that brackets in the text of this meme. So they look identical, so they are homoglyphs. Homoglyphs are characters or glyphs rather that look identical to each other but aren't actually the same. So of course in the case of Python, semicolons play a less prominent role, although it can still be used to cause problems for us by means of homoglyphs. But there are other homoglyphs which can be used, which can cause trouble for us, especially when they are used within strings or identifiers. So let's consider an example here. So it looks like a string is being assigned a constant value 3. Now all of us know that's ridiculous, until we realize those apostrophes that constitutes that string are not really apostrophes. They are some other Unicode characters. This one, in fact. So what appeared to be a string H turns out to be an identifier, a variable, an identifier with 3 letters. That's what it actually is. Though this is how, for comparison, this is how a real string would look like, with an apostrophe, with 2 apostrophes. So apostrophe and the Greek silly are homoglyphs because they look similar to each other. And yet another homoglyph which can be used in place of this to make it look as if it's a string is this one. This one is mentioned in the PEP 672. I got it from there. Here I have collected a few homoglyphs together. So the letters which appear on the same row are homoglyphs. As you can see, there's little to no difference between them. And this is only a very, very, very few select homoglyphs. You can find lots and lot more online. So homoglyphs can also be used to make trouble with the URLs. This has been used in the past, although now it's less easy to fall prey to these fake URLs, this URL spoofing or phishing. So as you can see, these 4 lines look identical, only they aren't. They all are different strings which differ in the first letter, which are these. But it's okay, as a matter of fact, because domain names translate to an ASCII form called Punicode for DNS purposes. So all except the first two does not go to google.com. It's something else. You can get this Punicode form using this in Python. So coming back to homoglyph examples, consider this example, which a function toss, which determines the outcome of a toss, of a coin toss, So if the coin turns up a head, so it is Alice's turn, and otherwise it is Bob's turn. So that means if it is not a head, Bob will get the chance. We can tamper with the head string and replace the E with a Cyrillic E, and it will still look the same, and none will be the wiser, because then Bob will always win the toss. An easy way to bias the function in favor of Bob. A good way to prank your friends. Okay, consider another example here. Here I have a function foo, which just prints hi, and then I try to use that foo function. I try to call that function, but I will get an error, because foo consists of only ASCII characters, Latin characters, whereas the foo that I have defined has the second letter as Cyrillic, which is a homoglyph of the Latin O. So that's another example. Another way of messing with Unicode is using with invisible characters, usage of invisible characters. So for example, in this code snippet, I compared two strings, hello and hello, but the result is false. Why is that? It's because the second string actually consists of 6 characters. There's an extra character, it's a second character, which is a 0-bit space. It's a special character in Unicode, which is used for scripts which does not have a space as such, and to facilitate with line breaks, where to put line breaks when they are being rendered, but that's something else. Okay, let's look at another version of our toss function. Here we can have yet another way of messing with this function to make it always favor Bob, like last time, by inserting a 0-bit space character after the H, or wherever, actually doesn't matter, somewhere in that string. Just make it something other than head. That's another way of messing around with this function to favor one of the players. So these are a few of the invisible characters present in Unicode. Okay, each of them have a specific purpose, but they can be abused nevertheless, like we have in the last examples. Another aspect of Unicode, which in Python, which is interesting, is the Unicode normalization in Python identifiers. For example, consider this example where I have a variable x raised to n, which is being assigned a value of 5. And then afterwards, without even defining xn, I'm trying to print the value of xn. So what could the output be? It might be an error, I guess, but it isn't. But it's the value of x raised to n itself, which is 5. So why is this happening? It seems that xn somehow got the value of x raised to n. Why? That's because xn and x raised to n are one and the same as far as Python is concerned, as is x subscript n. This is because Python does a Unicode normalization and converts the Python for the identifiers and converts it to a normal form while they are being parsed. So why is this normalization necessary? Well, we'll explain that with an example. Consider this 2 characters. They are one and the same, as Unicode sort of considers them as equivalent. Because Unicode has multiple different ways of writing the same character. So these 2 characters may look the same, they are effectively considered the same, but they consist of different number of Unicode code points. The first one consists of just 1 code point, whereas the second one consists of 2 code points, because a combination combinatory code point is being used. These are both the same characters, C with a cedilla, but they are formed in a different ways. So we need to consider them as the same. For that, we do normalization. After normalization, they are converted to a form which is one and the same. That's why this is happening. So now we come to the part where we'll see some things there. The bidirectional algorithm of Unicode plays a prominent role. So consider this example. Here I have 3 lines where the first line consists of just English characters, the ASCII characters, which are written from left to right. And the other 2 consist of Arabic and Hebrew letters respectively. So how will these characters be rendered? We type them like this, but will they be rendered as we type them? Well, no. The English characters will be rendered as it is, but the other 2, the Hebrew and Arabic letters, will be displayed in the right to left fashion. Observe that the direction of the angle brackets have also changed, but it's just the appearance. Those characters are really less than, not greater than. If you copy just the less than, the greater than part in the right side, the rendered version with the orange background, they will still be less than, but when they are being rendered, it will be displayed as if it's a greater than symbol. It's because when these characters are being rendered, they sort of look around in their surroundings and they see that the other characters are of a script which are written from the right to left. So they will also be written. These less than symbols will also be written, will be rendered in a way that is from the right to left. So they are sort of the non-letter values. They sort of go along with whatever the letters around them are going, to put it simply, in the case of a bidirectional algorithm of Unicode. So consider another example here. So there are 3 lines, and it looks as if the letter 3 is being assigned a variable value. So since Python allows Unicode in the identifiers, I used Arabic and Hebrew letters as identifiers, variable names. So it looks as if a variable is in the first line. It looks as if a variable is being assigned to a constant value 3. It doesn't seem to make much of sense. The other 2 lines seems okay though, but all these lines are not what it appears to be. It looks like this. It's because letters of a script which are written from the right to left are being used. It is when they are being displayed, the same thing as what we saw in the last example happens. It will be rendered in the right to left direction, even if regardless of the way how we actually wrote it in the source code. So the left part is how it is being rendered, and the right part is what we actually wrote. What we would have thought was a constant value being assigned a variable is actually the other way around. The variable is assigned the constant value 3. The Arabic letter ba is being assigned 3. And the second line, where we thought the Arabic letter, the ba, is being assigned aleph, Hebrew aleph, is actually the other way around. So let's take a closer look. The same thing happens in the last line as well. So effectively, these 3 lines can constitute a standalone valid Python code snippet. So let's take a closer look at the last line and see how exactly the characters are being rendered. So I have highlighted the part which corresponds to the source and the part where it is rendered. So it goes like this. First the bar is rendered, then the minus is rendered, then the opening parenthesis is rendered, but it appears like it's a closing parenthesis. Then the Hebrew letter aleph is printed, then 1 star, then another star, then 2, then the closing parentheses, which appear like a opening parenthesis. So it may look like it's exponential. It is 2 raised to aleph minus bar, but it is actually bar minus aleph raised to 2. That's it. So consider yet another example here. So this looks quite simple enough. So we are assigning the string with Arabic letter aleph and followed by a comment of some sort. Just some random comment. It looks like it's just some random comment, but in this case as well, appearances are deceptive, because the output turns out to be Arabic letter bar 5 times. But how could that be? The Arabic letter bar is in the part of comments. It's a comment, but not actually. It's just appeared to be in the comment. The source of this actually looks like this on the right side. The source is on the right side and the rendering is on the left side. So it's actually A is equal to bar 5 times bar with the aleph, the Arabic aleph in the comment. It's just that when it is being rendered, again by virtue of it, when it is being rendered, it is rendered differently. It is because the characters from these highlighted characters from the Arabic bar till the end of the comment, that part, just that part, is considered the algorithm that renders it determines that part needs to be rendered in the right to left fashion, because everything in between is either written in a script which is written from the right to left, or something called a kind of character which goes along with whatever is around them. So 5 and the special characters will go with the flow. So what really influences the writing direction are the Arabic letter bar in the string and the aleph as part of comment. So only that part will be written from the right to left when it's being rendered, and the A equal to part will be rendered as it is from the left to right part. So let's step through how it is being rendered. So as I said, that part will be rendered from the right to left. So let's see, first the A is rendered, then equal to, then we go to the final letter in the comment. So we are doing it right to left, then like this, then the hash, then 5, then star, then the string, and that's how it is. Observe that in some editors, most editors maybe, the syntax highlighting is a big giveaway. So in this case, the rendered version, the aleph, looks as if it is part of a comment. See, the syntax highlighting has carried over. So that is a giveaway sometimes, depending on the editor that you use. So there are ways to actually override the default behavior of rendering characters in using some sort of a control code called bidirectional codes, control codes. I have listed some of those codes in this table. We won't have time to go over all of them, but I will go to 1 or 2 of them. So let us see an example of the usage of bidirectional control codes, which can be used to override the default behavior of a bidirectional algorithm used to display the characters. I mentioned in the introduction of this talk that in the past people have used, or abused rather, the Unicode to make people believe that they are opening a document file instead of an executable file. Here I will give an example of how that was pulled off. One way of pulling that off. So these two names, file names, they look like they are the names of some innocent text or some innocent document. But it isn't so. once again, it is not how it looks like. It is not what it appears to be, because we use the Unicode override control codes. This RLO character it's a single character actually. It's not written as 5 letters. It's a single character with a specific Unicode value as listed in this table. It has Unicode value 202E. So it's called right to left override. What it does is no matter what has happened so far, it will force the character rendering to happen in the right to left direction, regardless of what characters are being used. So in this case, after the RLO character, RLO is the effect of an RLO character is terminated by the use of a PDF character, pop directional formatting, once again listed in this at the last of this table. In this case, the PDF character is missing, so the right to left override takes effect till the end of the line, end of this text. So let's see what happens. Let's step through how it's being rendered like we did last time. So first the A is rendered, then N, and the next N, and so far it goes as we are the way that we are used to. Now comes the right to left override control character. So that by itself doesn't make anything to render, but it influences the way the characters are rendered that comes after it. So the next letter is not T. Because of the RLO character, it will go to the last character and start displaying from there till the beginning of the RLO. So what it means is that the last E will be printed. Then it goes on from towards the left till the RLO character. So like this. So let's see a few other examples. So this is not how it appears to be. Once again, surprise, isn't it? Okay, right. So this is written in this way. By virtue of the same way that we saw in the last example, that everything that comes after the how, because of that RLO character, will be displayed in the right towards the left. So it renders as how aria, but it is written as how I era. But when it's rendered by virtue of that override control code, it will be displayed as how aria. Likewise, in the case of this Hebrew, but here instead of right to left, I use left to right, because Hebrew is usually written from right to left. So to make it the render in the right to left fashion, I don't need any override control character, because that is a default behavior. But if I wanted it to be rendered in the left to right fashion, I can use this RLO character, and it will be displayed accordingly. So to see an example where the PDF character is used, see this, just the middle example in the middle. So just the era part is overriding happens only for the word era. The rest of this is rendered as it is. So this PDF character is useful because these control codes, they can be nested. There is a limit, but that's a very generous limit. 200 something or something level of nesting is allowed. So that's it. So now we will look at some ways which can be of some possible help to alert us as to the presence of some of the tricks similar to that we have seen so far, like the use of control codes to override the default way in which the characters are rendered, or the use of homoglyphs with all this. Such things are hard to detect when we just look at it. But there are stuff that can possibly alert us that something is out of the ordinary and may be worth investigation. Here I will talk about a couple of ways which can be of help. These are not foolproof ways, but but can be of some possible help. I made two files, F1 and F2. F1 has just one opening curly brace, and F2 has an arrow followed by a closing curly brace. So when we look at a GUI text editor, F2 would look just like a opening curly brace. The F1 and F2 will look identical when you are opening a GUI text editor. So when we use a code review tool like a simple diff, it will show that what character is different. So that should be enough warning for us to see. When I try Vim diff to use that, Vim has an interesting property. It won't display many of these control codes, and it will instead display it as their Unicode values. Like in this case, 202E is displayed instead of just RLO. So that is often helpful to realize that these manual overriding codes are being used. So unterminator overriding Unicode override codes are usually considered bad, because that's how most of these attacks happen. Emacs GUI, it barely has any difference. It looks a bit confusing at first, because it shows that there is one character difference, but they look identical nevertheless. But when you try it on the terminal version of Emacs with Emacs -NW, it will show a bit more. It will show an underscore, which seems to mean that there is a control character base being used, an extra character is being used. So that can alert us. So another thing that can help detect the use of manual bidirectional override control codes is simply by looking at the cursor movements. If override codes are used, the cursor will simply jump from one place to another. Consider in this example, I have something which renders as "oh God," but it is actually "oh" followed by an RLO code with "dog." So it will be displayed as "oh God," but it is written as "oh dog." So when we are stepping through this character by character by the cursor of an editor, see in the right hand side, I have shown the position of the cursor. Can you see the cursor moving? Yeah, that's what I meant by cursor. Okay, let's start. So suppose we start moving the cursor from the beginning of the line. So it will go from O to after the H and to the beginning of RLO. But from that point, the cursor will simply jump to the end of the text. See, the jumping happens. So from that point onwards, the cursor will move from the right to left instead of from the left to right. See, so that's a good giveaway that something interesting is going on. Another thing that can help is syntax highlighting. Remember, we mentioned in the example for homoglyphs where a function name has homoglyph characters being used. So in this case, I have a function named bar where the A is a Cyrillic character and it's not Latin A. So in the case of Vim, as I have shown here, the identifier is not highlighted properly. This may or may not, this is probably not a feature, but maybe a feature as well. But in the case of Emacs, it is being shown properly. Again, this may or may not be a feature, I'm not sure exactly in this case. But depending on the editor, the syntax highlighting can also be of great help. And many tools which are commonly being used by the programmers are now taking into consideration the possible attacks that can happen by virtue of the presence of control codes or stuff like homoglyphs and invisible characters. And source forges like Git, GitLab, GitHub, Bitbucket, and almost all of them have got support to warn us as to the presence of control codes. And I hear that many compilers like GCC and Clang are now paying more attention to such possibilities, and are now considering adding new flags for producing warnings for the same. So we have come to the end of the presentation. The aim of this talk was to familiarize people who have not yet come across such possible ways of messing with Unicode, so that they will know when they see it that this could be somewhat happening. So this is quite honestly an area where pranksters can abuse a lot to fool around with people. And we won't know what exactly hit us if we don't even know the possibility of such things happening. So hopefully the next time you come across something like this, you will know, oh, this could be a possibility. So yeah, thank you. So if you got any questions, I'd be happy to take them.